programs run faster, and as developers, you do not suffer because you migrate to something, right? You're still as productive as you were. It just gives you options to make better decisions about how you want to run your applications, better decisions about which libraries and which ecosystems you want to run, right? It gives you options. It multiplies the options that you can have. Currently, GraalVM is a production-ready project. Several companies are using that. Many more are using that and not publicly talking about that. And you should take a look at that. So GraalVM currently, in the distributions that we have, it can give you several things. It can give you high performance for applications, specifically for the JVM-based applications in JVM languages. And it's a fact. We run tons of benchmarks. We're going to see some numbers today, and we're going to see some small benchmarks as well, just to make sure that there is no trickery, right? GraalVM has this low footprint mode where it can compile your applications ahead of time, and then it will run with different performance characteristics, right? It will give you incredible startup, and it will give you much better memory consumption that you would usually expect from running a JVM application. You can interrupt and have applications written in different languages, and there are a number of companies who are using these facilities. For example, one good use case for that is maybe if you have a front end for your application in something like React, you can do the React server-side rendering using inside the Java process using our JavaScript engine without losing performance. So it's a fast JavaScript engine. And you can embed it. You can put it into different contexts. You can run it within your large application, whether it's a native application or a Java application. And that could be probably out of those kind of the most niche benefit. But it's very cool if you actually have use for that. How does it work? In one picture, GraalVM is this runtime that has support for the languages, which I named before, so you can see the logos there. And it can run applications in different contexts. It can run it as Java applications in the context of OpenJDK. It can be running the applications inside Node.js environment. So if you have friends who write Node.js applications, you can share some information about GraalVM with them, and they can interrupt between JavaScript and Java. So you can give them your null pointer exceptions, and you can get back the typical the promise not handled errors or whatever is coming often from the Node.js, and you can build it into different applications. So we have some experimental builds of Oracle database where you can try that, and there is the JavaScript engine from GraalVM there, and you can run some JavaScript inside your database. Or you can run the same languages in a standalone mode, which will not depend on the JVM or Node.js. It will be this executable, natively compiled executable, just the program that you double-click on, and it runs, which is very convenient for several use cases. If we look at the scale of the project, which is very important, it's a massive undertaking, right? There are different parts to the GraalVM project, and they're very large. At the heart of the GraalVM project is the compiler. The GraalVM compiler that is written in Java. So if you feel like you would like to look at what it's doing to understand better, you can go on GitHub, open the source, put it into your favorite IDE, and then go follow the definitions and see what it's doing, or pretend to understand what it's doing. I do that every week. I try to do that. And then a number of languages. So all those components are kind of a little bit separate, right? It's a modular architecture, and it allows us to build this runtime, which is very efficient. And at the same time, it allows us to handle those very different languages, for example, with ease. So this is the general. Also, tools. Tooling is very important, right? Because we don't want to lose the tooling that developers use and love daily. Love and use daily. For example, Visual VM. If you want to monitor what your application is doing, so on GraalVM, you can do that with your normal tools, debugger, profiler, and so on. For Java applications, GraalVM has two distinct approaches how you can run applications on GraalVM. One is in the JIT mode, and that means that you will run your application normally using the OpenJDK distribution, using the Java hotspot virtual machine, with the just-in-time compiler replaced by the GraalVM compiler coming from the GraalVM project. This is the most straightforward application of GraalVM and how you can benefit from using it. So to use that, you just need to download it and run it. And also the ahead-of-time compilation mode, but we will get to that a little bit later. So one of the most important parts why I think the performance matters for developers, right? We all know that performance matters for operations and saving money on the cloud. That's kind of like very straightforward, right? If you need to buy more compute power, you pay more to your cloud provider, or you pay more for buying hardware. So the benefit of better performance there is very obvious, right? But for developers, there's a second level benefit, which I think is very, very interesting, right? It allows you to write code in the way that you want to write. How many of you recognize the idiom where you kind of hide the logger or hide some kind of computationally intensive operation behind in the if block? How many of you recognize code like that? Of course, we all have written code like that because we know that it's expensive to call the logger, right? And we know that it has to check conditions itself, right, inside the methods. But also we know that it's going to be slowing down our application. So we wrap it in double if blocks. How many of you have seen people doing something like using the explicit math or explicitly manually kind of optimized versions of the code rather than using something highly more abstract? It's a typical performance trade-off. Like people sometimes say, okay, this is slow. We need to rewrite that. And you sacrifice readability and maintainability of the code because a version where you have to juggle with bits or use math, it's much more error-prone, right? You would rather use higher abstractions. You would rather allocate data structures and use, I don't know, modern API, libraries, streams, right? You would like to write code that is easy to maintain and write. But unfortunately, the current understanding very often is that to write code that performs well, you need to abandon all those cool features and you need to go back to the kind of more explicit and a little bit more verbose and error-prone method of writing code. Chris Newland is one of the performance experts, and he recommends to his team to not use any complex features, not use abstractions when performance matters. So obviously, for us as compiler writers, as the project that is runtime, this is kind of like a very sad. It's our job to make your code fast, right? You should be thinking about writing code that fulfills your business value, right? That's business value, and we should make sure that it's fast. So GraalVM and the vision for GraalVM is that abstractions that you introduce to the code should not have performance regressions, should not impose any performance overhead on you, to allow you to write code as you want to write it without regretting the performance. So how do you achieve that? How do you run code that is abstract and also fast? You use GraalVM. It's very simple. To get started with GraalVM, currently, you just follow a number of steps. You go to the download site. You download GraalVM. It comes as a zip archive. It's tar.gz, but it's in the archive. You download it on your machine. You unzip it. You put the bin directory of GraalVM on the path, and you're done, right? GraalVM is a JDK distribution, so it comes with the utilities like Java and Java-C included, right? So you can just download that, use that Java instead of whatever you are using now, and expect your code to be faster.
You have to compile the code with GraalVM?
Yes, that's an excellent question. Do you have to compile your application with GraalVM? And the answer is no. GraalVM is a JDK, right? And it uses Java hotspot virtual machine to do as an implementation of the virtual machine that it runs. So it's compatible, right? It operates on the bytecode just as any other JVM would do, right? You don't have to recompile your application classes or your dependencies. Bytecode is bytecode, and that is the input to the JVM, and it runs really, really well. I'm going to show you a quick demo here, and I'm going to also show you a benchmark that hopefully kind of illustrates the point that maybe you don't have to sacrifice performance when you run your Java applications. So I have my cloud machine here, and it's a reasonably powerful one. It's kind of like a developer's laptop, 64 gigabytes of RAM and 8 cores and no monitor. So I'm gonna use the terminal. I have my Java here, and this is a GraalVM JDK here, right? So when I run Java version, I can see that this is a GraalVM version 19.3.1, which was released in January, running on the hotspot from OpenJDK, right? And it's a normal Java. What I can do, I can just run Java applications here. I will also show you that it's a JDK distribution. So if I do which Java, and I go to my folder here, right? Home, right? And then I'll look at the bin directory, right? You can recognize your normal applications. There is Java command, which we're going to use to run Java. There is Java C that we're going to use to compile your applications if necessary, right? And it's normal Java C as well, right? So you can compile things with GraalVM Java C and then run it on any other JDK if you wish to do so. You can also notice that there are some other commands that you will not find in normal JDK distribution, like, for example, to run JavaScript or to run Ruby or Python. This is our support for those additional languages, right? So we're gonna look at that later. But I want to run a benchmark here. I'm gonna go into the repository, and I'm gonna go into the a benchmark folder here, and this is my benchmark. I'm gonna cat source main Java IO control flow object hash. This is my benchmark. It's really simple, very simple. It's the same code that we actually saw on the slide. It's going to compute the hash of a number of fields. There are two methods. One is raw, and this is the explicit version that just does math. And the other one is the abstracted one, which calls object hash out of the same fields, right? And if you don't know what object hash does, object hash takes varargs, so there has to be some array initialization there. And then it uses arrays hash code, calls a method that takes an array, checks for null, and then iterates that array, and literally does the same thing that we have here written manually, right? So it's the same code, and it's supposed to do the same thing, but it's also having like layers of abstraction on top of that. And I'm gonna run this. I'm gonna run this, and I'm gonna just use this. I'm gonna just run this script like this, and this will be the only benchmark that I'm gonna run. So it's what? Everything hash, everything? Right, it's gonna take 20 seconds. It's supposed to do it in the opposite direction. First show you the normal OpenJDK, but that doesn't matter, doesn't matter. We can see that it runs the code, and it's not the most scientific benchmark, right? It runs for 20 seconds. Don't expect it to be like super rigorous. But we will see that the abstracted version, right, the hash abstracted, is not significantly slower than my object hash raw version, right? So we are measuring the number of operations per unit of time. The difference here is like at least, I don't know, like 1%. And given that it's run in the cloud for 20 seconds, they are almost equal, right? So performance of the abstracted version and non-abstracted version is the same. And I'm going to run with the Java 8 version of the same thing, right? I'm going to use OpenJDK installed with SDKman. It's 802.35. It's a modern version of OpenJDK. It runs code as you normally would expect, right? And we can see immediately that the performance results are different, right? The character of the performance results are different. When we run it on normal OpenJDK with C2 as a default JIT compiler, right? As you run, most probably you run your Java applications currently, right? You can see that the abstracted version is highly, highly less optimized than the raw one. We can also see that GraalVM is actually faster on this particular example than OpenJDK, but it's a minor point. Usually it's faster. But the major point is that there is no degradation from having manually explicitly optimized code and code that you would like to write for that. There is a question. You want to understand why? This is no. So the question is, and let's just repeat that for the camera and for you to confirm that this is a question. Why GraalVM is good at optimizing code like that? Which optimizations are used in this particular example, and how it works, whether it's a bytecode to bytecode translation or how it's happening, right? So how it's happening is probably the first question that we need to answer. GraalVM compiler. The compiler is the just-in-time compiler that is used within OpenJDK, right? That is used within the Java Hotspot VM coming from OpenJDK project. It integrates with the VM using JVM CI, which is the Java Virtual Machine Compiler interface, which was an interface added to Java 9. There was a JEP, I forget the number, but there was a JEP to add this interface. So if you would like to write a third-party compiler and plug it into your JVM, you would use that interface. So literally, you can think of it as having a method that takes in bytecode and outputs machine code, right? It outputs like a byte array with machine instructions. So the JVM runs your code. At some point in time, it figures, OK, this method is called a lot. Let me try to optimize that. And there are several compilers. There is first the Java bytecode gets interpreted, then it's compiled with a simpler compiler, and then there is the compiler with more optimizations. And the GraalVM compiler is a top-tier JIT compiler in this example, right? So at some point of time, the bytecode is given to the GraalVM compiler, and then it optimizes to machine code. So the difference we observe is because the machine code that GraalVM compiler produces is better. The question is now why? This is a complex question. For this example, right? There is tooling, and we don't have time currently, but there is an example if you will go and watch at DevOps Belgium last year in November. Thomas Rutinger and I did a deep dive into GraalVM. So we showed this example, but we showed it in much more detail. There is some tooling that you can use to look at what the GraalVM compiler understands about your code inside and see which phases, like how the code transforms on using the compiler graphs. And for this example, there are approximately 180 transformations that are applied on the compiler graph. It's not on the bytecode level, right? But there is internal data structures that I used. C2 uses the a graph as well, but it's a different implementation. And it's very hard to kind of pinpoint on the larger examples which particular optimizations are incredible. So mostly, the benefits from here come from two things. Escape analysis, and GraalVM compiler has an excellent escape analysis, right? It's a partial escape analysis, which means that we can avoid allocating objects on certain code branches. So the compiler doesn't have to prove that the object escapes from a method fully. So if you have an if block, right, and on one branch you just have a quick return, and on the other branch you have to allocate the object, C2 cannot do that, and GraalVM compiler easily avoids the allocation until it's actually needed. So that allows us to operate on the smaller bits of code, and then GraalVM compiler has really, really good inlining. Right, so those two together they go back and forth, because inlining more things, you get more vision what you can optimize, and escape analysis maybe again could do more things, right? And there are a number of optimizations like that, and it does the normal things as well, like every compiler, like dead code elimination and I don't know, some other things, right? No. It doesn't go through any LLVM thing. It's purely Java JIT, and it goes like that. We can talk about that later, and it's a little bit too technical topic for this. Right. So, but it just purely bytecode, machine graphs, and everything. Right. So this example, of course, is one benchmark which you should not trust, because I'm showing you this benchmark being on stage. But so don't expect results like that, something being like 4 times faster than it currently is just by switching the thing. Like it doesn't necessarily will be this way, right? Because hotspot and C2 is actually really brilliant piece of engineering, right? It's really hard to be faster than C2 when it's done its job very well. So why did we start with the start? So what I would encourage you to do is to get interested in this enough to go and check more. Where's my slide? Right, so this was it, right? Try your code, be open to seeing results, and also look at other benchmarks. One benchmark suite that we can recommend is the renaissance.dev, which is the benchmark suite that uses more modern Java workloads than maybe some other benchmarks that you've seen before, right? So if you look at that, there are a bunch of, there's some Akka, there is some Dotty, there is some Neo4j, there are some RX stream-like benchmarks, right? The code that we currently write, right? If you use some benchmarks which were written like 20 years ago, maybe they don't exercise the code patterns that actually currently are like modern Java. I'm not saying that they're not useful, but I'm saying that maybe they're hyper-optimizing for particular code patterns that were popular, I don't know, 10 years ago, or like 20 years ago. Java is 25 this year, right? Probably 25 years ago, we wrote Java very differently from how we're writing it now. So what I'm trying to say is that you should check more benchmarks, and more benchmarks are good, right? So optimizing for particular ones could be tricky, and also actually just trusting benchmarks is also not the best thing you can do. So I would encourage you to try it on your code, on sample code, or the code that looks like the workloads that are important to you, and then just see for yourself. If you think that the results the GraalVM shows are not up to your expectations, you should report issues to us. And you should, for example, I don't know, collect some information, some debug information, maybe a Java flight recorder profile, and send it to us. And we will look at that, and we can, well, before you start like manually optimizing your code, right? Removing allocations and not calling methods, you can just maybe send us some information, and maybe we can make it faster for everyone, right? So this is the JIT mode. It's very simple, very straightforward. Out of the box, it works with Java applications, and it's particularly great. Now it's time to go for the AOT. Do you know how much time I have? Approximately like half an hour. Very good, very good. We're right in the middle. AOT versus JIT. GraalVM, as I mentioned before, can compile your applications ahead of time to machine code. It uses the same GraalVM compiler, just without using it as a JIT compiler. If you think about that, as we talked before, you can imagine that the compiler has the interface that takes bytecode and a profile, right? And the information how this code is particularly being used at runtime, and outputs machine code. And then you can imagine that the profile is null. There is no profile. There is no information about how it works at runtime. So the compiler can still do this job. At least the signature matches, right? So GraalVM can do both JIT and AOT, and it comes with a performance trade-off, right? It comes with the different performance characteristics. So you can pick what you want. Typically, when people talk about performance, they talk about different things, and it's actually very confusing. When somebody tells you that something is fast, you never know what they actually mean. When somebody comes to you and says, Node.js is fast, do you know what it means? Do they mean that peak throughput, right, the amount of work that they can do in a unit of time is a lot? Do they mean that latencies are good, that it never stops, that all requests are served within like a very small amount of time? Do they mean that it starts really fast? And like Node.js is like an example, right? We love Node.js. We have Node.js in the distribution, so it's not mocking Node.js. It's just an example. Do they mean the memory footprint, right? Sometimes people say, oh, JVM is very memory hungry, right? And it's uncomfortable to run in the modern cloud environments because it needs a lot of memory. That might be true and might not be true, but this is the axis how people measure performance. So the thing is, the just-in-time compiler and just-in-time compilation does certain trade-offs, right? It needs runtime information. It needs the profile to do its job, right? So the startup and the warm-up curve of running in the JIT mode will be higher, right? You need to warm it up more. That's why, for example, when we run benchmarks, we warm up the JVM instead of just going from get-go and measure how it behaves, right? But it gives you really, really good throughput, and it gives you really, really good latencies, because the JIT compiler has the best visibility into what happens with your application at runtime. So it can employ like speculations and saying like, oh, we're gonna optimize this code in a specific way, and then if we are not right and some unexpected data will come, we will de-optimize and run a different version of the code, right? So just-in-time compilation has a lot of freedom in what it can do. And that's how it gets really good throughput. The ahead-of-time compilation makes a different trade-off, right? Ahead-of-time compilation means that all the code that you're going to use is pre-compiled, right? So there is no warm-up. You don't need to warm up anything because everything is already compiled. If everything is already compiled, you don't need to include the facilities for compilation, right? If you know that every code, like all bytecodes that you ever will be running in this application, if it's already in the machine code form, right, you don't need to include the JIT. You don't need to include the metadata for the class files. You don't need to include the memory for the JIT to operate, because like it will have to construct the graphs. Those graphs will take memory, right? So if you don't do that, you can shave like a large chunk of the memory from your application at runtime. So when you compiled everything ahead of time, your memory footprint will be better. It will be lower, and less memory consumption at runtime is better, right? But also, because of the nature of ahead-of-time compilation, sometimes you don't have the access to some speculative optimizations, because you cannot de-optimize. Because after that, you won't be able to optimize because you didn't include the compilation facilities, right? So you have to be maybe more defensive with your optimizations, and then maybe you cannot speculate that much, and then maybe your peak throughput will be lower. And the latency will be lower because latency is the reverse of the throughput, right? So if you can handle 10 requests per second, then yeah, your latency will be what? The reverse of that. So there is a trade-off to be taken. So you have to understand which way you want to run your applications. And luckily, it just naturally follows from what kind of applications are you running and in which environments. If you run it with beefy machines and you don't restart your applications for days or hours or months, if you know that the JIT will warm up and be excellent at what it does, you run it in a JIT mode, right? Because then the startup and warm-up costs are amortized over the runtime of your application. And it's absolutely great. And if you want to run your applications in small constrained environment, in containers, if you will, somewhere in the cloud, where you give it half a core and 100 megabytes of RAM, then probably you don't want to run in a JIT mode, because there won't be enough memory to even do the JITting, right? So that's where you prefer the ahead-of-time compiled version. So GraalVM can do both, and it's very easy. So in the JIT mode, we just run our Java application as normal, using our Java utility. And for the AOT, we're going to use the GraalVM native image utility to compile the application. So we will take all our classes, all our class files or jar files, everything. We will feed it into the native image utility, and it will output a binary. What happens during this process? Quite a bit, actually. Quite a bit. So the input is our application classes, the libraries and dependencies, right? The classes from the JDK, the whole Java code that is there, right? Also, as an input to that are the implementation of some virtual machine components that are necessary to run your code. When you run your Java application, you run it under assumption that memory is infinite, right? Because you know that you're going to run with the garbage collection enabled environment, right? So it would be kind of unfortunate if that quality would be lost at the ahead-of-time compilation step. So it includes, the native image includes the garbage collection implementation. It's also written in Java, and it's a part of the GraalVM project. and it looks at all that Java code in the bytecode form, right? And it analyzes it, and then it pre-initializes the classes, and then it compiles everything to machine code, and it writes it out in a file, and then it wraps that into the ELF executable wrapper, so your operating system knows how to run it. So currently we support, and we have distributions for Linux, Mac OS, there is Windows executables as of recently, I think. And there is also, we support Intel and AMD Arch 64. So you can do the same thing on ARM, in ARM environments. During the analysis, when we initialize the application, what actually happens is that the utility initializes the classes, and it constructs the full universe of classes and objects that will be used within the application. So this process currently takes a little bit of time, like a few seconds, maybe a couple of minutes. And it also, it follows and builds a graph which objects use which other objects, so what points to what. So it includes in the final executable only the parts that are actually used in the application. So everything that is not used in the application is not included in the final binary. And that is all done statically before we actually run the application. So now, because of that, and because the nature of the static analysis that is run, there are some things that you should be aware of. So it operates under the closed world assumption, so it needs to see all the bytecodes that will ever be executed in an application. Because there is no JIT compilation facilities, right? There's in the executable, there is nothing that knows how to work with bytecode or class files. So it needs to see all of that beforehand. And it needs to know that those classes are actually being used. So there are some features that you can use in your Java applications that kind of make it really, really hard to analyze statically. For example, you can use proxies, or you can use reflection to dynamically load or access classes at runtime. And it's impossible to statically figure it out. So as a developer, you can provide hints to the static analyzer saying, I'm going to use classes in my model package, and I'm going to access them reflectively because my data access framework does that. Right? You know that because you know what your application is doing. The static analyzer cannot know that because it doesn't know what your application is doing. So luckily, you can provide the configuration for all that. So you can configure reflection, you can configure Gen I access, you can configure proxies, you can configure including the resources. If you want your application to serve a nice cat picture to your users, you're not accessing that in the Java code using the new object dot method dot something, right? You load the resource, you load the bytes, and you send the bytes somewhere. So it's impossible for the static analyzer to know that you want to include this particular cat picture, right? So you need to provide hints to that. So the only kind of more imposing limitations of this approach, that there is no loading of new classes at runtime. The new classes, all the classes have to be loaded and initialized during the build step, during the native image generation, which is certainly possible to do. There are a number of libraries that support GraalVM native images currently, a number of frameworks as well, and you can put all the configuration on the command line like a real developer, or you can embed that into your jar files in the conventional place. And then you can ship your jar files to other people, and they will be able to use native image utility on that with more ease because they won't need to figure out the additional config that you have to provide. And all in all, this works, and it works really, really well. I'm going to show you an example of different application. Again, on my cloud here, on my cloud, I'm going to show you the application. What I'm going to show you the Micronaut application that I have here. It's a very simple application. src, main, Java, example, Micronaut, prime controller. Micronaut is a web framework. It's a web framework, kind of like Spring Boot, or kind of like Halidon, or kind of like, there are other frameworks, right? There are tons of frameworks in Java. It's very similar to Spring applications, right? It declares declaratively controllers and everything. So our controller here our business logic will be to calculate prime numbers, right? We just have a stream and we'll filter that stream, and everything that divisible by something is not a prime, right? So it's very kind of synthetic simulation of business logic. And I can run this application normally, right? I will run my java minus jar build libs. What's that? There's all jar, right? I can run my application. And it starts, and it's really, really good. Micronaut is kind of optimized for the startup, right? So they do a lot of things by using the annotation processors, and they try to do some configuration beforehand. So the startup is actually pretty decent. So it starts in 1.5 seconds. And what I can do, I can now use this application, and I'm gonna, 80 primes. We can compute some primes, right? So between 2 and 10, there are 4 primes, which is 2, 3, 5, and 7. And we can run with more things, and there are more things here, and we can also count them. This is our application here, right? Right? No, not count. Primes count. Let's not count primes. Let's just output primes. I don't remember the mapping. Right? So there are primes. It's an application that works. It's a good simple application. What I can do now is to run this. Not in the JIT mode. So this is using my Java. This is using my GraalVM JDK, right? Wait. Right. So which Java here is still my GraalVM Java. Now what I can do, I can use the native image utility. I can use the native image, and I can just feed the jar files to that native image. And that will take 2 minutes on this particular machine. So I'm not going to do this now. But the output of this is the application file. So it's a decently large file, right? It's something like 45 megabytes. But it doesn't depend on the JVM for the running, right? If we look at what it depends on, right? What it links against the operating system libraries, right? So there is no JVM for this, and when I run this application, it runs in a glorious 23 milliseconds. And also, like, just to show you, there is no trickery, right? It's still our application, and it's still running, and it's still outputting the same thing. So obviously, at this step, you could try to run some performance tests or something, and you will see that the throughput of the ahead of time compiled version is not as great as in the JIT mode. But more importantly, it's interesting to run the startup and memory consumption measurements, right? Because that's where you would like to use. That's the important parts when you run your application in the ahead of time compiled mode, right? So we're gonna do this, and for this, I'm gonna use this kind of nice script. Let me show it again, right? Cat plot test. I'm gonna run my application, and I'm gonna start recording the memory usage and CPU usage of that, and I'm gonna sleep, and I'm gonna ping the application, and I'm gonna sleep a second, ping my application, sleep a second, ping an application, 3 requests, 3 seconds sleep, and then it will kill everything, right? So this is what I do. This is what I'm gonna do. Plot test, complete, right? Complete, do I need? No, plot test, complete, like that, right? So it starts in 23 milliseconds, it runs, it pings, and there is now my application file here. So it's on the cloud, so let me just do the quick Python server so we can see this thing, right? This is my plot here. This is what we see. The memory consumption of this application is 48-ish megabytes of RAM for starting up a microservice that computes some prime numbers and outputs and prints them into the console, right? This is a minimal functional microservice, if you will, right? It responds to HTTP requests. It runs with 40 megabytes of RAM. The red lines are the CPU usage. You can see that CPU only spikes when we actually do requests, when we actually compute the prime numbers, which is very, very good. If we look at the examples on the graph like that for a microservice that are not compiled as a GraalVM native image, then the graphs will be a little bit different. So I think I have an example here. Right? This one. So on the left, you can see AOT. On the right, you can see AOT. The same, it's kind of a very similar graph that we had, right? So 40 megabytes of RAM and some CPU usage. And on the right, on the left, you can see the same application running in the JIT mode. So it starts, it still responds to the requests. It runs with the actually fairly reasonable 150 megabytes, right, to run 4 requests. It uses the CPU at the startup because it has to do a lot of initialization and things, right? And all in all, it takes a little bit more time because it's just slower at starting up. So if your environments are valuing startup and memory consumption, like if you run in the cloud in small containers, you should take a look at the GraalVM native image. You can also tweak some memory usage, which if you run it on your powerful machine, then you will see a little bit different picture. So the max memory heap, the size of the heap that it uses by default, is not limited. So if you run it on a beefy machine, you will also see that it takes 400 megabytes or something, because you're just not constraining that enough. So there are 2 keys that you would like to maybe play with: the max memory size and the young generation size. And the implementation of the garbage collection that goes into the native image is that before the young generation is filled, there is no garbage collection happening. So if you put young generation at 100 megabytes, right, it would at least use 100 megabytes, right, because there will be no reclaiming memory before that. So you can play with those keys. You can try it. You can enable the printing information about GC to see what's actually happening and see more results. There are a number of frameworks which support GraalVM native images. Micronaut. There is Halidon. There is Quarkus.io. This is the example that Burr Sutter showed at the keynote yesterday, where he compiled this balloon game and then used that. There's Spring Boot support is incoming. We're working with the Pivotal team, and Pivotal team works on that, and GraalVM team works on that to enable that. There was a question. Yeah, because frameworks could be very dynamic, right? Frameworks could do things very dynamically. For example, using reflection to initialize certain components or something, right? And then defer the class loading until the very latest point. And this is it's a normal practice, right? And it's not a bad practice. This is how just the code is written, right? So you could configure those things yourself, right? As an end user of the whole code, you see, you have all the jar files, so you can provide all the configuration if necessary, right? And there are tons of knobs that you can additionally configure, and configure how native image treats the code and cuts off certain code paths that you don't need. You can provide tons of hints to that, but for that you typically need to understand what your code is doing. So it could be hard if you use a framework that does a lot. Because you might not know what it's actually doing. You might have an idea what it deals with, but not the implementation details. So it's much better if you have the support out of the box. So those questions are figured by the engineers of the certain framework. And the results of which framework you use actually are not super important, right? GraalVM native image compiles the code, right? So whichever framework you use, or if you run your small command line application with normal Java, right? The startup of that thing becomes very, very small because everything is precompiled. The memory consumption also becomes much, much smaller. There are still differences, right? Because different frameworks do things differently, right? But the largest chunk of gain comes from using the native image ahead of time compilation. And the goal for us would be to, and us, I mean the GraalVM team, the goal would be to increase that and push the AUT compilation to the limit, so the throughput doesn't suffer that much. So currently you can employ the profile guided optimizations. When you build the native image, you can record the profile of what your application is actually doing, and then use that profile for generating a better executable, right? That will be better performing on that particular workload, right? And it's not a modern novel practice like languages that compile things statically use that forever, right? But this is one tool that you can use to increase performance of the GraalVM native images. So all in all, a few takeaways for just how to write your code, how to maximize the performance of your Java code. Typically, you would like to write small methods, right? Large methods are kind of awkward to optimize for JIT because small methods can be easily inlined in other methods. So going from small methods to larger method bodies is the thing that compilers do naturally. Splitting like a large method into like smaller methods is a little bit awkward. So if you write small methods, you give the compiler more chances to shine. So don't write large methods. The allocations are almost free, right? In very many cases, the escape analysis will not allocate objects if it's not needed. So like don't try to like cache objects in like static fields for like performance reasons. Like unless you actually know what you're doing, right? And that's the usual disclaimer, right? You don't want to hand optimize if you didn't study how it behaves with the compiler, if you didn't look at what transformations are happening in the compiler graph. I know that it's hard for like you have other things to do. Like this is not your business job, right? So reach out to us, right? And we'll be happy to look at it. And if you want, there is a trade-off for the throughput, GraalVM in the JIT mode, for the footprint, GraalVM in AUT mode. There was a question? So is there something different using between the garbage collection on the GraalVM versus OpenJDK or versus? Yeah, so GraalVM runs, the virtual machine implementation is actually Java hotspot. So it's the same JVM implementation that is in OpenJDK. It's just the just-in-time compiler is different, right? So you have access to the same garbage collections, and the same garbage collection will run. There is necessary integration between, the compiler needs to know about the garbage collector, right? Because in the machine code that it outputs, it has sometimes, it needs to like output certain memory barriers for the garbage collection to work, right? So there's things that you will need to configure, right? But currently, the parallel garbage collection works, the G1 GC works. I'm not sure about CMS. The Shenandoah, for example, doesn't work with GraalVM compiler because the barriers are missing. So that support is not yet there. But by default, you can, if you just run normal OpenJDK, you just convert and it works. Epsilon is not supported as a GC. But it's an engineering problem, right? So it's something that's fairly easily to be solved because there are compilers that work with those garbage collections, right? So it's just the matter of figuring out where to put the barriers, right? And there are many parts to GraalVM. If you run JVM applications for JavaScript or native images, it's production ready. You can use it. People are using that in production. There are some parts that are experimental and visionary. Twitter is using the GraalVM compiler for their Scala microservices. They show really, really good results. So people who were doing Scala, just take pictures. I mean, download and try it. But there was not recently, actually a couple of months ago, the Oracle Cloud Infrastructure team rewrote some of their services to switch them to use the GraalVM. And they saw peak performance and garbage collection time improvements. And the migration was really, really seamless, right? It's a compatible thing. There was this collaboration between NVIDIA and Oracle to create this GraalVM language on top of GraalVM to expose CUDA GPU bindings to languages that work on GraalVM, which is very interesting. And it won't improve performance of your Java applications, but it's really interesting because it gives you the power of using GPU very naturally through the same interrupt protocol to all the languages that we support. If you want even more, then you can look at the Oracle GraalVM Enterprise Edition, which is the product by Oracle. It will come with an even better just-in-time compiler that can give you better performance. And there are some security-related features, additional ones. It's compatible in a way that it runs the same applications that the open source project runs, right? So you can, if you don't want to use the Enterprise Edition, you can always not use it. And it comes with support. So if you want to, I'm not sure what's the process, but reach out to your Oracle representative and talk about that. And just download it, just try. Follow the development. If you don't want to do it now, we are working hard on making it better and better. We are releasing new versions, major versions every 3 months. There is quite a bit of improvement in all directions. It's a very fascinating project. People are using that in production. Maybe next time we meet here, you will be some of the people who are using it in production as well. Thank you very much.